In this video, I introduce Wasserstein generative adversarial networks. Given two probability distributions, PR and PG, we want to find a metric to measure their difference. Once their difference is smaller than a criterion, they cannot be distinguished by any distance matrix. Wasserstein distance is such a distance metric that is defined as infimum expectation of x minus y over gamma, where pi is a set of all joint distributions gamma, whose marginals are PR and PG. The infimum above is not what we need to train generative models. Instead, using the KR duality, the infimum is converted as a supremum, where the supremum is overall the K-Lipschitz functions f. If the supremum is attained for some w, we can calculate the distance between PR and PG. If we have a parameterized family of functions fw, we can solve the following maximum problem to compute the distance. The problem is how can we select the function fw. Given two metric spaces x with distance dx and y with distance dy, if a real constant k for all x1 and x2 in x satisfies the following relationship, k is defined as Lipschitz constant, and f is defined as K-Lipschitz. Namely, if we cannot measure the difference of two distributions, we can map them into a latent space. And then we can use this relationship to calculate the maximum distance between two distributions in the domain X. We select F as a critic network with the parameters W, similar to discriminator in regular GAN. Critic FW is used to train the generative model. Different from the discriminator in the regular GAN, the critic FW is used to compute the maximum distance between PR and PG. A generator G theta is used to generate PG close to PR to minimize the distance. The derivatives of W with respect to model parameters theta and W are computed by using two equations. This pseudo code. The first part is used to train the critic network, and the second part is used to train the generative network. When the loss function is reduced during the training, Wasserstein distance also becomes smaller, namely the generative model distribution is close to the real data distribution. To ensure that FW is K-Lipschitz continuous during training, the parameters W is clamped in a small window after each gradient update, which leads to a compact space. For instance, the real and fake densities, both Gaussian distributions, have different supporting space, namely they don't have overlapping in space. A regular GAN discriminator results are vanishing gradient, and the generator cannot learn anything because vanishing gradient. We need to add noise in real or fake density to make the GAN discriminator work. However, the WGAN critic can train the model with a linear gradient without noise injection. For more details, please check with this references. Thank you. Bye.